Welcome to the second of our two-part installment, taking a continued look at strain sensing. This lesson focuses on strain compensation techniques. One of the issues often encountered when using a strain measurement system is that the values I'm measuring are often affected by things other than just strain. Temperature is one of the primary effects of this nature. As the temperature changes, say in the lab in which I'm using my strain measuring device, as the temperature is changing, the temperature can change the resistivity of the material of which the strain gauge is constructed and can affect my measurement, affect my strain measurement, even though it's induced by a change in temperature. Let's take a look at this effect analytically. We'll start off with our original definition that delta R, the change in resistance, divided by R, was equal to the gauge factor times the strain, epsilon. If I think about this in terms of temperature now, I could redefine this gauge factor times epsilon as being equal to TCR, the thermal coefficient of resistance, times delta T, a change in temperature. So TCR, that's my thermal coefficient of resistance, and that's typically defined in parts per million per degree C or per degree F. And my delta T, that's my temperature change over the course of the measurement. Here are a few example TCRs based on the material. You can look up from a data sheet, let's say, the parts per million per degrees Fahrenheit spec. Constantan is one of the more common materials that strain gauges are going to be constructed from. That has a relatively small TCR, only about 6 parts per million per degree Fahrenheit. Compare this TCR to the TCR for an isoelastic material. Those are going to be on the order of 200 to 300 parts per million per degrees Fahrenheit. And compare that to something like nickel, that typically has greater than 1,000 parts per million per degrees Fahrenheit. So you see then one of the main reasons this Constantan is so popular is it has this relatively low thermal coefficient of resistance. So we can calculate an equivalent thermal strain that is a result of this temperature effect. It's induced by the thermal coefficient of resistance of the strain gauge itself, not a strain imparted on the strain gauge. So this epsilon EQ for equivalent, comma T, is because it's a result of a temperature, change in temperature. Epsilon EQ, comma T is equal to TCR, the thermal coefficient of resistance, times my change in temperature divided by the gauge factor. So the gauge factor for something like Constantan, for example, is typically about 2. An isoelastic alloy is something like 3.5. So let's plug in some numbers here. We'll use an isoelastic alloy. So we have a TCR of 260 parts per million per degrees Fahrenheit. And let's just look at a 1 degree change. So we have a delta T of 1 degree Fahrenheit and a gauge factor of 3.5. This is going to be equal to 74 microstrain. Now, this sounds like a small number, microstrain, but if the system I'm using, if I'm expecting a small strain to begin with, these numbers can add up rather quickly, right? With 74 microstrain, and we're only looking at 1 degree change in temperature, right? If you walk in the lab on any given day, from the doorway to the back of the lab, that could be a couple degrees swing. So this number is significant. So as a result, the strain measured by my strain gauge is going to give me an actual strain. Let's call that an axial strain, just to give it a name here, epsilon sub A, plus a strain, a component of the strain due solely to the change in temperature. So the next question then is, well, is there a means to compensate for these temperature effects? Well, to answer that question, let's consider a beam of material again, subject to an axial load. And we're going to laminate our strain gauge on top, and we're going to align the long axis of the strain gauge with the axis of loading. And so what we're saying is that this strain gauge is going to be subject to an axial strain, epsilon sub A, plus a strain associated with a change in temperature, epsilon sub T. If I were to measure strain in this configuration, I would have a temperature-induced effect. So one way to circumvent this or account for this effect is to have a second slab of the same material, now not subject to any loading. My second strain gauge is now only subject to the temperature changes. So these two slabs will be co-located, so they're experiencing the same fluctuations in temperature. But because my second slab of material is not being loaded by an axial load, it'll only be subject to this strain induced by a change in temperature. We can set those two strain gauges up in a bridge circuit, where I have my active strain gauge, so this strain gauge up top here, in position 1, and I have a compensating strain gauge down here in position 2, and then I have static resistors in position 3 and 4. So I've effectively constructed a half bridge with an active and compensating strain gauge. Let's take a look at my transfer function, my ratio of my output to input voltages. Here I'll start with the description of a full bridge, and we'll just set strain 3 and 4 equal to 0. So I end up with V out over Vi is equal to the gauge factor all over 4 times the quantity epsilon sub 1 minus epsilon sub 2. Epsilon 1 in this case will be equal to epsilon sub A, the strain due to the axial load, plus epsilon sub T, the strain due to the equivalent thermal load, minus epsilon sub 2, which will be, once again, the strain due to the thermal load. So my epsilon sub T's will cancel, and I'm left with a description of the output voltage divided by the input voltage equal to the gauge factor over 4 times my strain due to the axial load. So in this setup, I've used a second strain gauge that is co-located with the original strain gauge, such that measuring the same changes in temperature, but this second strain gauge is not actually seeing any axial loading. And using this setup then, I'm able to compensate for any temperature changes that both of the strain gauges experience. So now let's consider compensating for things other than temperature. Let's consider here a beam of material, and I only want to measure the axial strain. But in this case, not only do I have an axial load applied, that's my force F, I also have a moment applied. So this piece of material is being stretched and bent. So in this setup, I'm trying to measure my axial strain, epsilon sub A, while simultaneously rejecting any bending strain, epsilon sub B. So one way to accomplish this will be to mount strain gauges on both the top and the bottom of the beam. This top strain gauge, that'll see an axial strain plus a bending strain, and the strain gauge on the bottom, that'll see the same axial strain, but now minus the bending strain. So with an appreciation for the strains imparted on the gauges, we can now consider where do we put these strain gauges in our bridge circuit to try and get these bending strain terms to cancel. If we write down our full bridge equation, the transfer function for the full bridge, what we see is that we need these strain terms to be located at epsilon sub 1 and epsilon sub 4. We need them to add. So what we'll do is configure our bridge such that epsilon sub 1 is equal to epsilon sub A plus epsilon sub B, and epsilon sub 4 should be equal to epsilon sub A minus epsilon sub B. In this setup, we only have two strain gauges, so at the same time, we could set epsilon sub 2 and epsilon sub 3 equal to 0. So if I plug these in, I'll find my transfer function is equal to the gauge factor over 4 times the quantity epsilon sub A plus epsilon sub B plus epsilon sub A minus epsilon sub B. So these epsilon sub B terms, they'll effectively cancel each other out, and I'm left with a description now of the output voltage divided by the input voltage equal to the gauge factor over 4 times 2 epsilon sub A, the 4 and the 2 will cancel, and my final description will be the gauge factor over 2 times epsilon sub A, the axial strain. Now that we've derived the fundamental math, we could see how this will transfer into hardware. So here is our bridge circuit. We have an R2 as a static resistor and an R3 as a static resistor. And then we've gone ahead and put our strain gauge up at top in position 1 and the strain gauge underneath the bar in position 4. So the question here was, well, can we compensate for things other than temperature? So based on that compensation that we were attempting to accomplish, we wrote out the transfer function for the full bridge circuit, and then we evaluated how we could apply strain gauges to the bar and what positions of the bridge we would apply them. such that we get the requisite terms to cancel. In this case, we wanted to reject the bending strain, so we wanted the epsilon sub b's to cancel. And then we were able to sketch out the hardware and decide if we were actually going to build this circuit, where the resistors and strain gauges would need to go in the circuit, such that we would reject the bending strain and measure only the axial strain.